Okay, well, we're going to move on and try to cover as much of modern atomic theory and bonding as we can in the time remaining to us in this semester. You do have a homework assignment. The homework assignment is this 11.1 questions 1 through 6. It's a standard Dropbox assignment, so it's pretty fast. Now, the first thing we need to understand is the nature of energy and light. That's where we got to begin. And so the first question really is, what the heck is light? Can you answer that? Well, light is a form of radiant energy called electromagnetic radiation, and it moves like a wave. And in a vacuum, its speed of movement is 3 times 10 to the 8 meters per second. All light moves at the same speed. Now, you may not recall this, but we did talk a little bit about the way atoms were organized way back, like the second week of school. And we didn't go into the details of how they were organized. We talked a little bit about them, but not much. But we know that somewhere inside atoms are electrons, protons, and neutrons. This one gentleman, Rutherford, came up with an idea. And his idea was that the nucleus was composed of protons and neutrons, and the electrons were buzzing around in some sort of a cloud. Well, that's the problem. We don't really know where they are according to Rutherford's model, all right? And it turns out that they're not just randomly buzzing around in a cloud. What are they doing? Well, let's see, if they were buzzing around in the cloud, well, why aren't they attracted to the nucleus and collide with it? I mean, you know, nucleus is positive, electrons are negative. So that's a real problem. Rutherford didn't have any explanation for how that would be possible. And so he thought maybe they were in a cloud or maybe they were in rings like a solar system, but he honestly didn't have an explanation. Now, we're not going to directly go to the model, a more modern model of the atom. We need to understand something about how people had the idea that there was some organization inside atoms. And in order to understand that, we need to learn more about electromagnetic radiation. Now, electromagnetic radiation is basically a form of light. However, not all electromagnetic radiation is visible. So things like X-rays, gamma rays, ultraviolet light, we can't see. There's a bunch of different colors of light that we can see, but it's a relatively small amount of the total different types of electromagnetic radiation. So we got to understand the properties of light. That's one of our key things to sidetrack. And the other thing we have to do is we have to understand why when energy is added to substances, so if you hit a chemical with some energy, why does it glow a certain color? Why do you see with fireworks, sometimes when the fireworks blow up, you see green lights or red lights or purple lights or whatever? Why? So these we got to figure out. And these are the keys that are going to lead into coming up with a new model for the atom that explains the organization of the electrons. Now, here's some of the properties of electromagnetic radiation. You probably have heard about these somewhere, you know, through middle school or maybe not. But anyway, it moves like a wave. It moves at the speed of light in a vacuum. What was that again? Oh yeah, 3 times 10 to the 8th meters per second. The distance between the peaks or the valleys is called a wavelength, all right? And frequency is how many of these wavelengths would pass a certain point per second. So if the wavelength was really long, since all light moves at the same speed, it would have a lower frequency. Not as many would pass per second. If the wavelength was very short, so the peaks were close together, since all light moves at the same speed, more wavelengths would pass per second. So peaks passing a point per second is frequency. Now, we have to continue trying to understand light a little bit, but I want to talk a little bit about visible light because this is actually important to the whole way that this was figured out. Now, you notice I wrote red, orange, yellow, green, blue, indigo, violet, and then I abbreviated it Roy G. Biv. Well, those refer to the colors essentially that you see in the rainbow. Now, it's written in the backwards order that you see here that, well, what is shown here is the wavelength. So red here has the longest wavelength, 7 times 10 to the minus 7 meters. which is 700 nanometers. And that also will have the lowest energy. And as you move from the long wavelengths towards the short wavelengths, you see different colors. And by the time you get down to violet light, the length of a wavelength is 4 times 10 to the minus 7 meters, or 400 nanometers. And down there, it's higher energy, the wavelength is shorter, and we're talking about violet light. Now, if you go off this end of the spectrum, so that you keep getting smaller and smaller and smaller wavelengths, you keep getting more and more and more energy. Ultraviolet is more energy than the visible light. This red through violet is considered visible light. And you can see only a small part of the whole spectrum of wavelengths of electromagnetic radiation can actually be seen. Ultraviolet is more energy. X-rays, which you get if you get an X-ray, are more energy. And gamma rays are even higher energy. And at the other end, as the wavelengths get longer and longer, bigger and bigger, you have things like infrared light. Then you move on to microwaves, like your microwave oven is bombarding your food with electromagnetic radiation that has a wavelength of 1 times 10 to the minus 2 meters. Okay, so that's in the centimeter range. And then finally, you even have things like radio waves, which are very, very long. So you might have 10 to the 4th meters per wave. That's a lot of distance between the two peaks of a wave. So this is a little bit about light. You really should know the order of the colors of light, Roy G. Biv. Know that the Roy end is the low energy 700 nanometer end. That's where red is. And if you go down to the IV end, where there's violet, it's much higher energy, and it's about 400 nanometers in terms of wavelength. Now, in order to understand this modern view of the atom, we need to understand what happens to matter when energy is added. So what happens if you heat up a nichrome wire with a Bunsen burner, or add energy to like a neon light, or perhaps you add energy to specific elements or compounds? Well, what you'll see is, and you can stop and watch the video here, but what you'll see is that they glow specific colors. It turns out every element has a different, specific colored glow. Every one. No two are the same. Now, how does this make sense? Well, what happens is if you look at atoms that you saw in the video, they emitted specific wavelengths of light. So lithium was red, copper is green, sodium is kind of yellow. Why? Well, only certain specific energy transitions, that's the movements of the electrons inside an atom, are allowed. And they are unique for every atom. Now that got us thinking that, well, look, if only certain changes of energy are allowed, there must be some organization inside the atom. And you can see kind of the idea here is, if you look at energy, you've got maybe a lithium atom that you zapped with some heat. Some of the electrons inside the lithium atom might change position to become excited, and then if they drop back down to a lower energy position, like when you remove them from the heat, what happens? Well, energy is always conserved. So if you've got high energy here and low energy there, the energy has to come out. It has to go somewhere. So in this case, the way it comes out is in electromagnetic radiation, which is red light, which is why lithium actually glows red. If you have a different energy transition for copper, that's why it's green, and you have a different energy transition for sodium, that's why it's yellow.